This is section 4.4, exponential and logarithmic equations, part 1. So thus far, we've looked at exponential functions, we've looked at logarithmic functions, and we looked at some of the properties of those. And so now we're going to use that information to solve equations. So on this second slide, we're going to look at solving exponential equations by expressing both sides of the equation with the same base. So here with the if b to the n power equals b to the nth power, what they're showing you is if I can get the same base on both sides, then I know that I can take the exponents and set them equal to each other. Okay, so I have 5 to the x power equals 25. Now, off the top of your head, you might be like, well, I know that 5 squared equals 25. But let's say that it was a value that we weren't as familiar with, right? So remember, my goal is to get the same base. So on the right side, I'm going to try to get a base of 5, which if I wrote 25 with a base of 5, it would have to be 5 squared, right? So notice that I didn't change the value of anything. The only thing I did was rewrite 25 with the same base that was on the left side. Because the bases are the same, I can now just write the exponents equal to each other. Remember, the goal here is to get both of my bases the same. Okay, I have 9 to the x power equals 27. So probably the first approach that somebody might take, since we were just talking about getting the bases the same, is they would say, okay, 9 to the x power equals 9 to the something power, right? And they are trying to make it equal to 27. Well, if you were to go ahead and start taking 9 to each power, 9 to the first power is 9. 9 squared jumps all the way to 81. So I don't have that option, right? So now I have to look at, okay, well, I don't have that option to express 27 as 9 to an exponent, but let me look at that number 9. Can I express that with a similar base that I can express 27 with? So 9 is 3 squared. So again, I did not change that value. All I did was express it differently. I expressed it in exponential form. And then skip this. And we say 27 is 3 cubed. Remember, when we have an exponent raised to another exponent, it's multiplication there. So this really looks like this. My bases are the same, right? That's what I was going for. So I can drop the base. 2x equals 3. I'm solving for x, so I would have to continue on. Divide by 2, divide by 2, and we get x equals 3/2. Because this is an equation, I can plug it back in and solve for it, right? So let's check it. There we go. 9 up to the 3/2 does indeed equal 27. So I would check it just in case somewhere along the way, you messed up your math. But anytime we're dealing with equations, definitely check your work and see if when you plug back in the solution, if it truly does make that true statement. Let's try another one. Okay. So 8 up to the 3x minus 1 power equals 64. So remember, my goal here is to get the same base. So what I'm looking at is 8 and 64. I want to try to see if I can express 64 with a base of 8. But 8 to the second power is 64. So that worked out. So I would rewrite this as 8 up to the 3x minus 1 power equals 8 squared. Did not change the equation. We can't do that. Otherwise, we're solving for a different equation. I'm only expressing 64 differently. Because my bases match, I'm going to set my exponents equal to each other. And then we would solve for x. I'm going to bring this over here. Divide both sides by 3 to isolate that x, and I get x equals 1. So solution set is 1. Sorry, that's supposed to be a 1. Okay, but I still want to check my work, right? That checks out. So that would be my answer. But I definitely plug it back in. I have 9 raised up to 2x equals 27. Remember, the first thing that I'm looking at is, can I express 27 with a base of 9? I can't, right? 9 to the first power equals 9. 9 to the second power jumps all the way to 81. So my next step would say, okay, I can't express 27 with a base of 9, but can I express 9 and 27 with the same base? And I can. 9 and 27 both can be expressed with a base of 3. So 9 is expressed as 3 squared. I can't forget my exponent, otherwise now I'm changing the value. So I'm going to keep that exponent. And then 27 is 3 cubed. Okay, I'm going to go ahead and simplify my exponent on the left side. My bases match. Therefore, I know that my exponents have to be equal if both the left and the right side are equal. So set this equal to each other. So I get x equals 3/4. That's what I get, but I'm going to check it. So I'm going to go straight to my calculator as equal 27. So we're good to go. Okay, let's check out that right side. So it says 25 raised to x minus 1 is equivalent to 125 raised to x. So now I have exponents on both sides, but still what I'm looking at is the bases, right? So I would say, okay, well, can I express, I'm going to look at the bigger base. Can I express 125 with a base of 25? $25 to the first power would be 25. 25 squared would be 625. So that jumps way past 125. So that's not going to be an option. So now I'm going to look for what base can I express both 25 and 125? Well, 5 squared is 25, right? So that can replace 25, but I cannot leave x minus 1. I have to bring that down. And then 125 can be expressed as 5 cubed. Again, I'm, just saying these, but get your calculator out. What I did up here in the right corner, you can do in your calculator really quick. You could say, okay, well, you probably are more familiar with 25. So you could say, okay, 5 squared, that's 25. Well, let me see with 125. Let's do 5 squared, or 5 cubed, 5 to the 4th power if we still didn't reach that number. And you can keep playing with those bases like that. Okay, I'm still going to account for my x from up here. So be very organized in your work because it's very easy to leave those outside exponents behind. Okay, we're going to simplify here. So remember, this goes to each one. And let me show you another way that you can write this. Because my bases are already like that, I can simplify here, or I can go ahead and write this. Just make sure that you bring it down properly, because if you just bring down 2 in parentheses and don't put x minus 1 in parentheses, you're going to forget to distribute it. Okay, continue to solve. Okay, so we get negative 2 equals x, same as x equals negative 2. I think that's my answer, right? But I'm going to go ahead and check it. We get the same answer, right? So that's just giving you scientific notation answer, because there's a lot of zeros before that 6. after a decimal, but it's okay. I don't even have to worry about, as long as my answers match, then I know that, yep, okay, -2 is indeed my answer. So this one makes us have to recall back to how we can express or what happens with negative exponents, right? So how I can express a base that's in the denominator with that same base on the other side of the equation that's in the numerator. So over here I have 4 raised up to the 1 minus x. And before I do anything else, I'm going to go ahead and take 64 and I want to bring it up to the numerator. So let's recall, right, if I have 1 over 64, the exponent to 64 is 1. Yes? I need to move this base up to the numerator. So I'm going to move it up there, but do you remember what happens with our exponents? We would use this rule to get rid of negative exponents, right? So the same way that we would move it to change a negative exponent to a positive exponent, in this case, we're trying to move that base, but the rule still applies with the exponent. So now my exponent would be -1. So 64 to the -1st power. Okay. If I was, this might be more familiar with you. If I had 5 to the, x to the -3rd power, I'd say, oh, you got to go to the other side of the fraction. So remember, this is like over 1. So it'd be 1 over x to the +3rd, right? And so that was just one of our exponent rules where, okay, if we have a negative exponent, we move the base. The sign of the base does not change, but that sign of the exponent then changes from a negative to a positive, or if it was positive, it would change to negative, right? So right here, we're focused on the base and we're moving the base so that we can get this, but we have to remember what happens with our exponent. The signs change. So I have 64 to the -1st power. My question would be, okay, can I express 64 with a base of 4? Because remember, my goal is to have the same bases. And I can express 64 as 4 to the 3rd, still bringing down my base, right? And so now I have 4 raised to the 1 minus x. I noticed in the notes that it has you first establishing 64 in the denominator as 4 cubed, and then bringing it up into the numerator. And that's okay. You can do it that way as well. As long as you're doing both of those steps, you can do it either way. So remember, there's multiplication here. So this would be to the -3rd power. So now I can drop my base. I have 1 minus x equals -3. Start solving for x by subtracting 1 from both sides. I'm going to move over here. -x equals -4. I can make that connection that x has to equal 4 in order for -x to equal -4, but let's finish it off. So x equals +4. Oh, did I enter that wrong? Oh, okay. It's in a decimal, right? There we go. So I just pressed F to D to see it as a fraction. Okay, so again, pulling a lot of things that we learned before out of our toolbox. So now we have 9 raised up to x minus 2 over 6 equals square root of 9. But remember, I'm trying to get the bases the same, right? So I can express the square root of 9 as 9 to the 1/2 power, and I'm going to explain that. If I have a radical, I would take this number right here, which is called the index, and I will bring it over here, and that will be the denominator to a fraction. Okay, so we don't see any numbers on this, right? So I'm going to write the numbers in. because there's not a number here, we understand that to be 2, right? We understand this to be the square root. If there was a 3 there, it would be the cube root. If there was a 4 there, it'd be the 4th root. But because there's no number there, we understand, let me get a darker color, it to be square root. And then 9 is not raised to any power. Well, we don't see it, right? So we understand it to be raised to the first power. So what I have here is 9 to the first. Okay, so I'm going to bring that 2 around and I'm going to plop it underneath there. When I do that, I'm writing this as an exponential form. So you have to get rid of that radical, and that's why the square root of 9 can also be expressed as 9 to the 1/2. Okay, I'm going to give you another example. If this was, I don't know, 3, and let's say we said the 5th root of 3. This would be the same as, remember, we don't see it, but there's a 1 there. If there was a 2 there, right, I would, in fact, let's put a 2 there. Let's say that it was the 5th root of 3 squared. So that 5 comes around and it would be 3 to the 2/5. That's the equivalent exponential form of 5th root of 3 squared. Okay, so going back to our problem. So now I have the same bases. That worked out nice because I had a 9 underneath the square root. So drop my bases, set my exponents equal to each other. Okay, I can start solving for x a couple different ways. I'm going to use cross products. So I know when 2 fractions are equal to each other, then their cross products are also equal to each other. So I know that the product of this has to be equal to the product of this because that's just a characteristic of 2 equivalent fractions. So 2 times x minus 2, make sure you remember to put x minus 2 into parentheses, otherwise you won't distribute it, equals 1 times 6. Distribute, 2x minus 4 equals 6. Start isolating that x. 2x equals 10. Divide both sides by 2, and I get x equals 5. I'm going to pause it just for a second to put it in the calculator so I don't waste that time. Okay, so here I entered into the calculator, 9 raised up to, I filled in x with what I solved for, 5 minus 2 over 6, that came out to 3, and then also I put the square root of 9, also came out to 3, so that means I solved correctly. So now we're going to use logarithms to solve exponential equations where we can't set the bases equal to each other. So in the previous examples, we would look at the bases and we'd say, okay, how can I get the bases the same? And if I can get the bases the same, then I can drop the bases and set the exponents equal to each other, right? When we cannot get the bases to be set the same, we're going to use the properties of logarithms. So right here it shows some of the properties that we've discussed. So one of the properties was with the exponents, dealing with the exponents, right? We said, okay, if I have the natural log, that ln is natural log, the natural log of b to the x power, that's equivalent to pulling that exponent down to the front and expressing it as x times the natural log of b. Okay, so that's one of the things we can use. Also, if we have the natural log of e, now if you're seeing this and you're like, yeah, I have no idea where this is coming from, then I would definitely recommend going back and looking at 4.3. But if I have the natural log of e, remember natural log, so ln is the same thing as log base of e. Okay, so if I have log base of e and then of e, so you have e here, then it cancels it out and the answer is just the exponent. And then the last example, or the last property that they show, is common log. So when we don't see a base, we understand that there's a 10 there. So same thing, if that base is the same as the number we're taking the log of, then whatever the exponent is, that will be the answer. So This cancels all of it out. Okay, so let's go ahead and look at some problems where we'll use those properties. Okay, so 3 to the x power equals 7. So if I was starting this problem from the beginning, the very first thing I would think in my head is, how can I express 7 with a base of 3? Okay, well, that's not going to happen, right? Not easily. So I'm like, okay, well, can I express 3 and 7? Remember when we couldn't express the other number with that number, the other number on the other side, this 3 as the base? Then I would say, okay, well, let me take both bases into consideration and see if there's a number I can express both of them with that as the base. Well, that's not an option either, right? So this would be the case where I'd say, okay, what I do to one side, I do to the other. That's always our rule in equations, right? So in that same fashion, I can take the natural log of both sides. Okay, once I do that, remember that I can pull out this to the front. So x times the natural log of 3 equals the natural log of 7. The point is to still isolate the x. So if this was x times 5, you would tell me to divide by 5, right? To get that 5 out of the way since it was being multiplied by x. The same way that we will divide by natural log of 3. You will not put natural log of 3 into your calculator just yet. You'll leave it alone. You're going to get some crazy long decimal answers, so just leave it alone. What I do on one side, got to do it on the other. And I would get x equals natural log of 7 over natural log of 3. That is my exact answer. The reason that is my exact answer is because I cannot express the natural log of 7 as a nice solid integer. And neither can I for the natural log of 3. So the only way to get the exact number would be to express it that way. If they want an approximated answer, then I would enter into my calculator and then just follow directions on what they want me to round it to. So natural log of 7 over natural log of 3. I get 1.7712, yada, yada, yada. It keeps going, right? Let's say that they said approximate out 3 decimal places. I would look at that 1 after the 7. I'd say, okay, the next number is 2, so it's not going to round up. It'll stay the same. So it would be approximately 1.771. Now that's only if they ask for an approximated answer. In my math lab, it is usually in that small blueprint. Okay, they want us to solve the exponential equation, express the solution in terms of natural logarithms. So they're telling us to use the natural log. And then they say use a calculator to do a decimal approximation for the solution. So they want us to approximate to 2 decimal places. Okay, so we don't even have to worry about, oh, can I express, either side with the same base? Because they just right off the bat told us to use natural log. So I'm just going to put natural log in front of both sides. Okay, then we'll take any exponents and plop them up front. I'm going to move down here. So now I have x plus 2, times natural log of 2 equals natural log of 404. I'm going to slowly start bringing everything away from that x, right? I'm peeling it away like layers of an onion. So I have to peel this outer layer, the multiplying by the natural log of 2 first. Okay. Now I'm left with x plus 2 equals natural log of 404 over natural log of 2. I'm going to subtract 2 to isolate that x completely, and I'm going to subtract 2. Because I'm subtracting 2 after I divide it by the natural log of 2, that fraction is not going to be interrupted, meaning that I'm not going to put the minus 2 inside the numerator or the denominator. No, I'm saying whatever that equates to, then I'm going to subtract 2. So x equals the natural log of 404 over the natural log of 2, whatever that value is, minus 2. It says, what is the solution in terms of natural logarithms? So they're asking us to actually answer it with the actual natural logs involved. So I would put make sure you're putting ln instead of capital IN. That's usually something very frustrating that the students experience. Okay, and then they want a decimal approximation. So I'm going to punch that into my calculator. It is, but I look to the right and I see an 8. So that means that my 5 will round up, making it 6.66. That would be my answer, my approximate answer. Oops. So here they tell us to use natural logs on both sides. And so we know to jump to that right away. But I want you to take a look at something. So because there's an e in this equation, I know that if I take the natural log of e, that I can drop that natural log of e, right? And it's equivalent to just the exponent. So I want to isolate the base of e, not from its exponent, but anything that's messing with it, right? Anything that's intruding on being on that same side. So here I'm going to divide by 7. And I'm doing that because I want to get this guy by itself with the exponent. Okay, so divide by 7, divide by 7, I get e to the 4x power equal 124. I paused it and put that in my calculator. Now that I'm here and I have e by itself, now I'm going to take the natural log. So notice that on the other ones, we just took the natural log, right? Because I didn't have e in any of my bases. But here, because I have e in a base, I want to move anything that's in the way from me doing this. So natural log of e, that's what I was going for. And then because I did it on one side, got to do it on the other, right? Well, I know once I get the natural log of e, I can drop that, and now it's just equivalent to 4x. Now on the other side, it's still natural log of 124 because that doesn't cancel out. I have to have the natural log of e. So if you see e in the bases, you know, okay, let me move anything away besides the exponent, anything away from that base so that I can take the natural log of it. All right, so now I have, let me pull this up here, 4x equals natural log of 124. I'm still going for what x is equivalent to, so isolating x, I'm going to divide by 4. Do that same thing on this side. I get x equals the natural log of 124 over 4. They asked me what the solution is in terms of natural logarithms. What they're saying is, okay, so if you weren't able to simplify your natural log to a straight integer, then what is the answer, the exact answer, right? And in this case, it was natural log of 124 over 4. Then they ask for the approximated solution. So this is where we'll punch it into our calculator and then round it out to 2 decimal places. I get 1.205 and some extra, right? And remember, that keeps going even past where the calculator shows the end. But it's only telling me to take it out to 2 decimal places, so that 0 would round up to a 1 because of the 5. So my approximate answer is 1.21.